So we were talking about 60 gigahertz millimeter waves, and I don't know if any of you remember how many millimeter is 60 gigahertz. Anybody remembers how many millimeter is 60 gigahertz? So 300 is the speed of light, right? 5 millimeter, right? Exactly. So 5 millimeter wave, and this is why it is called millimeter wave. And since it is such a small wavelength, there are many things that we talked about its properties, such as it needs very small antenna, it cannot go very far, and so on. And therefore, it is used for short distances like this, or going from there to text. So these are the applications. Mostly, it is for cable replacement for high definition streaming video. So now some people ask question as to why do you need 7 gigabits per second in your home? And really, there are very few applications that need that much. So they came up with this high definition uncompressed streaming video. I don't want to see uncompressed streaming videos. You see, the thing is, every day that you're watching the video in your home, it's all digital, it's all compressed, and it's all okay right now. But there might be some applications, but this is where it is going, is high definition uncompressed streaming video. Maybe in the studio they need it, but at home probably it doesn't. Interactive gaming, yes, that is where, if you have basically if you're doing some gaming and you want to see the action right away, all that is one. High speed file transfer, yes, when I'm doing the file transfer, I want it fast. And then mesh backhaul, which is shown in this picture. Now, this is not very short distance, this is long distance. And so what will happen is you will have to send a lot of power for it to reach here, because it is very short wavelength, it gets attenuated very fast, but then you can use it for high speed, if you can get there. So there was a lot of activity back in 2009 or 2005 onwards on this band, 60 gigahertz band. At least 7 standards were developed. And just 2 years ago when I gave this class, I discussed 4 of these standards in the class. This year I'm going to discuss only 2. And next time when I offer this class, there will be only 1. Because with time, we know what is going, what is coming. Okay? So 2 years ago we were not sure, and we discussed, I think, the first top 5, or maybe not top 4. But now we are sure that these are not going anywhere. The only thing that is going anywhere is 802.11ad. Okay, so we will discuss that today. The next thing that is having some mileage is wireless HD. And wireless HD was actually the leader all the way until 11AD showed up. Okay, so 2 years ago when I did the product search, I found everything wireless HD. This year when I did the search on Amazon, there is only one product that showed up wireless HD. Everything else is 11AD. Okay, so wireless HD is on its way out, and I'm presenting here in this class simply because there are some concepts which I think are interesting that will be helpful when we talk about other protocols such as LTE. So I'm going to take those aspects of wireless HD. And here's Google Trends. So another thing I do is figure out where the world is going. Is Google Trends, and this was done actually last week. So you can see ECMA, which was one of the first standards, is going nowhere. It is not even leaving this. This is in this color, by the way. You can't even see that color in the line. It is just only here, 0. Right? 802.15 3C is somewhat yellow. And again, I cannot see that line mostly. So most of the things that I see here are wireless HD, which is red, which was really high in 2009 and now coming down to 0. Y gig and 802.11ad are same, by the way. So Y gig is the product name for 802.11ad, and those are the things that people are searching for. Now, this Google Trend simply says what people are searching for. It doesn't say people are buying it. But if people are not buying it, they're not searching for it. Yeah.
Is the product name of 802.15 Zigbee?
3C is what?
Is that Zigbee?
No, that's not Zigbee. That is a 15.4. And I will come to that Zigbee thing later on. By the way, the 15 has many versions, which we'll discuss. And IoT requires very low bandwidth and very low power, which is different than 3C, which is very high bandwidth. And power is, actually not that much of an issue. So you see, no one is interested in ECMA anymore. Wireless HD was hot in 2008 and 9, but now being taken over by AD. And when I did the product search, I found 2 or 3 products on YHD. YHD is the wireless HD, right? And 10 to 15 products are Y gig. Okay. 2 years ago, we could not buy anything on 1180. This was not there, right? But in 2 years, things have changed. So today, when you go to Amazon, you will find lots of products on 1180. And in fact, you can buy a laptop and then the cards for that laptop. These are all available right now. You can buy a docking station which doesn't require a wire from HP and Dell. So all these 4 products are using 1180. Okay, and they call it tri-band products. Why tri-band? Because these same 1180 products also do 11AB, G, and AC. So they do 2.4 gigahertz, they do 5.8 gigahertz, and they do 60 gigahertz. Tri-band. So there is no single product like you cannot just buy 60 gigahertz alone. I mean, right now people cannot justify the cost of having 2 connections on a computer or 2 connections on anything. So with one chip or one card, you can get everything. Like this card, 11N plus Y gig. Okay. And this is actually wireless HD product. And this is the only thing I could find this time on Amazon. Everything else has disappeared. I went to the wireless HD website. They are still showing 10 products, but those are historical. Those, I think they haven't changed the website since 2009. They haven't updated the website, since it was at this peak. Most of those products I checked on the manufacturer website, they don't exist anymore. So there's only one, and this is actually, I don't know. Basically, it costs about $150 or $200 to replace a cable, which is right here. This is my HDMI cable. I don't know whether I want to pay $200 to replace that cable. And so it's not very interesting. But these are just general products, and the cost is incremental because I need 11N anyway. So I might get that 3-band rather than 2-band. So that's why 1180 is happening. So what is 1180? So 1180, instead of basic service set which we used to have before, BSS, now we have personal basic service set, PBSS. And these are group of stations that want to communicate. So in one room, you might have many PBSSs because you may want to communicate with your TV and somebody else may want to communicate with their TV or with their whatever devices. So you could have PBSS. And each PBSS has a central point like access point, but it is called PCP. And PCP provides the scheduling and timing using beacons. So basically, this is the one which does the access point job, is telling, okay, now this is the start of the cycle and who gets what when they can transmit. So each frame, so this is a beacon and this is another beacon. So in between is beacon interval. So this is called super frame. Okay. The super frame consists of beacon time. This is where the beacon is actually not just instantaneous. Beacon happens for quite some time, so it tells you some other information about the network. Then associative beam farming time. This is the time where you find out who is where, in what direction. If I want to talk to her, I have to do some adjustments, and I have to talk to her, I have to do adjustments, and so on and so forth on this side to him. So all that is happening in the associative beam farming time. Then announcement time. These are common announcements, which most like multicast, and then data transfer. Okay. So beacon time, associating beam farming time, ABFT, announcement time, and data transfer time, DTT. Data transfer time. And more details are coming up about each of these. So only PCP can send a beacon during the beacon time. So you cannot have multiple beacons, otherwise it will be confusing. You can have multiple networks in the same area and they will have their own beacons. But one PCP. In the associative beam farming time, PCP performs antenna training with its member. So if I am the PCP, you guys are the members, I will talk to one by one to each of you, figure out where exactly you are located. Everything is directional here, right? Everything is very directional. So I cannot be facing this way and talk to him, right? So basically, I will have to tune my antenna position to figure out how to talk to station 1, talk to station 2, talk to station 3. That is what ABFT time is. In AT announcement time, PCP polls members and receives non-data responses. So the next time, that announcement time, I can ask, do you have something to say? You say, I want to send something to B, to that station. So and I need 5 milliseconds. So I will poll every one of you and figure out what is your requirement. In AT, PCP polls, okay. In DTT, all stations exchange data frame in a dedicated service period or by contention in a contention-based service period. So you might have, just like we had real-time and non-real-time application in 802.11 earlier part, where we had what we call point coordination function, PCF, and distributed coordination function. PCF has a dedicated time. Nobody else can transmit during that time, and that is reserved for you. And the distributed coordination function is the time when you have to do RTS, CTS, etc. Here we don't have RTS, CTS, but we have this thing which is called contention period. So we have two periods, dedicated period and contention period. And during DTT, stations either use distributed coordination function or hybrid coordination function. So distributed coordination function is the original 11 thing, and hybrid coordination function is the 11E with priority of service and all that, right? So HCF and DCF, we have discussed this before. So back to this slide, you have this one. This is the contention period, and this is the dedicated period. So if you get a dedicated allotment, the PCP will tell you that your time starts at this time and end at that time, right? In the announcement time, it will all be told. And then when the time starts, you know exactly when you can speak and for how long. All right. So the beacon. Any questions about the previous one? Yeah.
Does this like SP and PCB be always like divided? I mean, always after each other, or can be mixed?
Right. The question is this time divided, or this is determined by just chance?
Yeah.
Right? That's the question. So the first part is clearly divided. First part is the SP part. Dedicated part is well defined. Right? The contention part, the details are coming up a little bit later. Okay? But there is it cannot be a fixed interval though. I mean, basically it has to be, everybody has a different length. So how that happens is somewhat parallel thing. For example, you can talk to him while she can talk to me. I mean, like basically here things are directional. So there are a lot of parallel transmission. Right? Yeah.
Is the PCP one of the stations they're talking, or is it its own dedicated?
Okay, so that's the idea, is that PCP is not a device that you can buy or you would buy. One of the stations which is most powerful will become the PCP. So for example, if you have a computer and several other things, the computer will become PCP. If you have a television and everything else, then television will become the PCP. So the idea is that you don't have to buy a separate device. Okay, but it is a separate function. So another thing that you should know is the function versus packaging. PCP is a separate function. So you could define a box which just does that function and nothing else, which is possible. But how do you justify in the real world that one, right? So that's why generally PCP is built into the devices. In the previous case here, this computer would be PCP, or the docking station could be PCP, or somebody who is central to everything. Both of them have the capability, but one of them will decide that, okay, I'm not going to be PCP in this network. You be the PCP.
So the one that has PCP on it, it still follows all of the rules that the PCP dictates.
Right. So the thing is, if suppose it is a PCP and of course it is a station as well, so it will have to basically decide all of those things. So it will say, okay, I need 2 seconds to transfer to this person at this station, and when should I be allocated? And that will be allocated. Yeah. So a PCP, a station could have both functions, which most likely it is a station as well as a PCP. Good. All right. So the beacon. Now the problem with the beacon is, where should I transmit? If I transmit in this direction, this person will not get the beacon. Right? So I have to say the beacon many, many times. So you see, there is this color beacon. This color is not representing here the wavelength. It is representing the direction. Okay. So because stations are in all directions and they will not be able to hear if I am facing the wrong direction, therefore the beacon has to be done many times. Although they are omnidirectional, one beacon is transferred to every antenna configuration. Okay, the antenna configuration is coming up in a minute. Yeah.
So what is these omnidirectional antennas? I mean, these antennas.
Yeah, right. Because the thing is, at this time we don't know exactly where you are, right? So I mean, I cannot beam form at this time, right? So I'm going to just send it in all directions here, but then I'm going to move and say in all directions here, and so that is coming up, right? It is not very narrowly focused at this point. Now we have to narrow it down. Right? Antenna training. Each station finds optimal antenna configuration with its recipient using a 2-stage approach. So first we start omnidirectional, then we find out you are roughly in this area, then we go into that area and do exact much narrower. Because if we do much narrower in the beginning, then I have to do a lot of efforts. Right? So I first take big area and then divide maybe 4 and then divide into 4, something like that. So we do in 2 steps. So first we do sector level sweep. So I can divide 360 degrees into 4 sectors or 3 sectors or whatever number of sectors. If I divide into 3, that is 120 degrees. If I divide into 4, that is 90 degrees. So I first try to figure out which 90 degree you are in, which sector you are in. And then once you find out the sector, then you find out which direction in that sector you are in. Sector level sweep, it sends in all sectors and finds the optimal sector, and then beam refinement procedure finds inside the sector what period you are in. So this is the sector level sweep. Initiator sector, it sends the frame out, and then it gets the feedback. Responder sweep. Responder is also. So the thing here is the interesting thing. I am trying to find where you are, and you are trying to find where I am. So you are going to be rotating around, and I am going to be rotating around, and at some point we will meet. We will be able to hear each other, right? So this is the initiator, this is the responder, this is the feedback and the ACK. Okay, and now we know exactly which sector we are in. Question.
Realistically, how long does this take?
Oh, this is all few milliseconds. I mean, thing is, this is could be done in microseconds and milliseconds. So it is not seconds, and there is no physical movement either. So there is nothing rotating. It's just electronically rotating. Okay. All right. Here is a picture which is better depicts this thing. So this station has decided that I am going to have two sectors, and I'm going to try 1 and 2. And this station is also deciding 2, right? And then once they decide which sector they are in, then they will decide subsectors, which part of that sector you are in, right? Depending upon the position. Right now, as I've drawn the picture, I think this will succeed, the first one. Everything else will be less power. Yeah.
Is that a way to make sure that it's not pointing at a wall and you're getting a reflected signal?
Yeah, see, the thing is that would be much lower quality. I mean, like, the thing is, the reflection will kill it. Direct signal will be much more strong.
But say it uses the strength of the signal to determine.
Yeah, right, yeah.
And
Yeah.
also the frequency and other parameters. It's not only
So frequency will not change that much, but the thing is, I mean, because we are going to do it in the same frequency band that we are in, right? But if we are moving, then yes. If we are moving, then the Doppler effect will change the frequency and other things. But everything else which is not direct will be lower speed, lower amplitude. Okay. So here is what is meant by sector level and subsector level beam refinement procedure. So this is the sector level sweep, and this is the beam refinement. All right. So this is like a binary search, and then actually, I mean, these signals that we are sending, they are properly coded so that you know who is sending, who is receiving, what direction they are sending, what direction is being received, and all that. So you can figure it out that you're talking to the right person, the right thing. Here is another example. So the initiator and left has 3 antennas with 2 sectors. Okay. So notice this one. This thing has 3 antennas, and first antenna has 3 sectors. So 1.1, 1.2, and 1.3. These are the 3 sectors. One antenna can move into 3 sectors, right? Second antenna has 3 sectors, 2.1, 2.2, 2.3. Third antenna has only 2 sectors, 3.1 and 3.2. So not all antennas have to have equal number of sectors. So on the PV, for example, very few things will be talking from the back. Most of the things will be talking from the front. And so there is no need to have too many sectors in the back. And the front, we want to be much more precise. So that's the idea, is that basically not every antenna configuration will have equal number of sectors, and the sectors could differ from antenna to antenna. So 3, 3, 2 example. The responder right has 3 antennas with 1 sector each. So this one has only 1 sector, and 1 sector. Okay. So initiator performs 3 sweeps with 8 frames, each using a different sector. So the 8 frames are these 8 frames. One will go here, one will go here, one will go. So you can see 3 plus 3 plus 2, 8 frames. And it will do this 3 times. Because first time, hopefully it is trying to talk to RA1. Second time, it is talking to RA2. Third time, it is talking to RA3. So basically, all possible combinations have been tried. Right? After these 24 combinations, we will know which is the best direction for antenna. For this one, it will know that it should be the antenna 1 in configuration 2, sector 2. Right? And this will figure out that this is antenna 1, sector 1. So we try all possible combinations. First we exchange, okay, I have 3 antennas with so many sectors, and this one says I have so many antennas with so many sectors, and say, okay, all right, so let's do this many exchanges. Yeah.
Does he use different antennas for receiving and transmitting?
These antennas, okay, so all the antennas do receiving and transmitting. That is given, right? I mean, you don't need a separate antenna. Okay, and if it is an antenna, it is doing receiving and transmitting, right? So you can have multiple antennas, right? And you can have them facing different directions, and you can divide those directions into sectors, right? So some antennas, they just whole thing is one sector. For some antennas, they can do this, this, and this. Yeah.
So it only has one sector each the receiver because of a hardware thing, not because it's the receiver.
Oh no, nobody is a receiver. Everybody is a receiver and a transmitter. I mean, the thing is, it will be difficult to think of something that doesn't transmit anything because it has to transmit an ACK, right? So in this configuration as here, I just arbitrarily assume that this is a transmit initiator, and this, actually we don't even use the word transmitter. Initiator and the responder. So whoever says, okay, I want to transmit to you something, can we align our antenna? Right? So initiator is whoever takes the lead. Right? And they are both, and this one actually in this case, yeah, they are. This is transmitting and this is receiving, but I think the same configuration, or if you want, you could do the other way around too. Generally, the same configuration will work in the other direction. Sometimes it doesn't actually, and in those cases you will have to do different one. But in this case, I think most likely it will work. Okay, in some cases where when we come to other cellular networks, in cellular networks they use different frequencies for uplink and downlink. Okay, if you do that, then you have to do it in both directions separately. Here, if you are using the same frequency, then they will have the same behavior. Any other question? All right, so now you see what new comes up with millimeter waves. Right? Directionality is a lot of problem. Directionality was good, but directionality has its own cost. So what if there are many PBSS in the same area? So they overlap. This is called a cluster. So now what will happen is, this is one little network in this room, and this is another little network in this room. They will get together and say, look, we got to use this thing together, so we are a cluster. Okay? In the cluster, one PCP will try to do things so that it doesn't affect other PCPs. Other PCP will try to do that, they don't disturb other people's PCPs. So that is what the cluster is about. So overlapping PBSS avoid interference by electing a SPCP, synchronization PCPs. There is another boss. On the top of PCPs, there is another boss which says, okay, all right, PCP number 1, your turn, PCP number 2, your turn, PCP number 3, your turn. All PCPs select the beacon interval to be an integral multiple of that selected by SPCP. So now everything has to be aligned, synchronized, right? So you get one slot, you get 2 slots, you get 3 slots, but everything has to be multiple of slots, so that it's easy for us to go back and circle again. Okay. Otherwise, if you do 1.5 and you do 2.3 and you are 3.3, we may not come back to the same number, right? So integral multiple of that selected by SPCP, non-overlapping beacon transmitter interval, and all PCP allocate service period in their schedule for BT of all other PCPs. So what that means is beacon transmission of all other PCPs. All other PCPs hear all allocations and avoid overlapping scheduling. So now let's go back here. So when I send my beacon, I send my beacon to my people, but also to the other PCPs. Okay? And they know that the station 1 is going to be transmitting, has been allocated transmit to station 2 in my this one, right? So if their station 3 is right there, they will know not to disturb that part. So there's a lot of coordination required among PCPs for simultaneous transmission. And so all the PCPs hear other PCPs allocations. That's what it means here when it says all PCPs allocate service periods in their schedule for beacon transmission of all other PCPs. Right? So every PCP has to hear every other PCP. So it's like this: if there are stations, there are managers, and there is a senior manager. Managers have to know everything what other managers are doing. If they don't know what other managers are doing, they could mess up. Right? All PCPs hear all allocations and avoid overlapping scheduling. Any questions about this so far? Yeah.
So for the SPCP, does that normally replace one of the other PCPs, or does it?
Okay, that's another function. No. So basically, SPCP could be a PCP also. Similar question. So SPCP is a function that could be done by a PCP and a station. So in one particular box, you could be SPCP, you could be PCP, and you could be a station as well. Now, spatial frequency sharing. This is another new concept with 11AD, and actually with 60 gigahertz, not with 11AD. 60 gigahertz, and that applies to all of the other standards as well, that multiple transmission may be scheduled on the same frequency at the same time if they don't interfere. So if I am talking here in this direction, they can talk in that direction, they can talk in that direction. They're not interfering because everything is very directional. Right? This could not be done with A11N to C, AC, ABCD to AC, but it's AD. Now everything is directional. So you could have multiple transmission in the same room, in the same network at the same time, and the same frequency. And PCP asks station to send results of directional channel quality during an overlapping service period. The stations measure the channel quality and send to PCP. So what that means is that if I allocate station 1 to talk to station 2, at the same time ask station 3 to talk to station 4, after you guys are done, tell me how was it? Did you hear a lot of interference? Did you hear a lot of interference? They say, no, I didn't hear anything. Then I'm okay. Then we know that, okay, these stations are located such that they can be allocated in future. If they say, no, there was too much bad, this was bad, then okay, so now we won't give you the same time as them. So basically we learn, after the transmission, we learn what was the quality, and you report it to the manager. Yeah.
Can you have to pair stations because it's so directional, or can you send to multiple stations?
Okay, you cannot. See, the thing is now, because it is directional, if you want to do multiple stations, what do you have to do?
Relay?
Well, either relay it or, you have to just change the direction. Multicast is not easy. PCP then knows which station pair can share the same slot. So after a few trials, we know who can be given to who can talk in parallel. Okay, any question? Okay. Now there are relays. And relays have the same function. They take receipt from one station and send it to another station. It is quite possible that this station cannot talk to that station directly because there's a dog sitting in the middle. Right? We saw that picture. So there is no direction that they can talk. So there could be a relay in the middle. Again, a relay does not have to be a separate box. It could be a function, which could be in every box. But then somebody could relay the frames. So link switch relay, MAC relays that act like a switch. They receive complete frame from the source and send to the destination. And link cooperation relays which act like a hub. Now, I don't know how many of you remember the difference between hub and the switch. Anybody knows the difference? Now, this has nothing to do with the wireless. In the Ethernet days, we had the Ethernet hubs and Ethernet switches. Does anybody remember the difference?
Doesn't the hub send one signal to all ports?
Yeah.
And switches doesn't.
That's a good one, yeah. So he says that one sends the signal to all the ports and the other switches don't send it to all the ports, they just send it to the right port. So actually another way to say the same thing is that hub is a layer 1 device. It doesn't know the frames, it doesn't know the destination, it doesn't know anything, it just knows the bits is coming in and goes in every direction. So it's a physical layer device. Right? And if the frame is half, it will send half frame to everybody. The switches are smarter than that. Switches take the whole frame in, look at the destination, and send it to that place. Right? So that is the difference between here relays. Link cooperation relays and the link switch relays. Switch relays will receive the whole frame and send it to the right direction. Cooperation relays will take bit by bit and send it. I mean, it doesn't have bit by bit, but at least it is not by frame, it is less than a frame. Very little buffering. All right, so there are two kinds of relays. So that brings us to the end of 822.11 AD. And 7 key points. First is that centralized scheduling. Only PCP can send the beacon. It sends beacons in all sectors, so it has to send it multiple times. Then there is a super frame, which is the beacon interval, which consists of the beacon time, associated frame and beam farming training time, and the data transfer time. Announcement time is used to collecting the request, and the data transfer can be pre-allocated or by contention. Antenna training is a two-phase process, sector level and beam level. And then there is this spatial sharing, parallel transmission, and there are relays. Okay? Any question about any of those 7 points? None? Then we are done with this lecture for today.